Today we're going to be looking at an osmosis and diffusion demonstration that involves both science content as well as math. The science content will focus on the osmotic process of the movement of water from a high concentration to a low concentration. For the math part of this lesson, we're actually going to be concentrating on what we call percent of increase and decrease. To be able to have numbers to work with for our percent of increase and decrease lesson, we need to really understand the mass of our egg. So here I have a basic egg and a digital scale. It's already been zeroed out, so all we need to do is place the egg on the scale to calculate the mass of this egg. As you can see on the scale, the mass of our egg is about 60.3 grams. We're going to go ahead and remove this shell from the egg using a basic chemical reaction. To begin, we're going to need a container in which we can place the egg. See, egg still has the regular shell on it. We're going to go ahead and use some vinegar that I have in this container here. Now, as the vinegar comes out of the container, what we'll begin to see is the process of the eggshell actually reacting with the vinegar. What's actually going on is the calcium inside of the egg is reacting with the acetic acid in the vinegar. We're going to go ahead and fill this container up until we're a little bit over the top of the egg. I've completely covered the egg now with our vinegar, and as you can see, there are little bubbles that are starting to form. We'll go ahead and zoom in, and you can actually see the formation of the bubbles down here. This is where the little sites of nucleation are occurring, and the egg is actually starting to break down. The calcium is starting to be decomposed based on the vinegar's acid. As you can see, we can see lots of little bubbles that are starting to form on the outside of our eggs. You can see them on both eggs that are in this container. So we're going to go ahead and move this container off to the side. It's going to take approximately 24 hours for the eggs to dissolve completely in here, and so that we have their shellless eggs at that point, and we're able to see the semi-permeable membrane. So here we have an egg that just came out of the vinegar solution. It's been sitting for about 24 hours. One of the things that I've gone ahead and done for this egg, just to kind of demonstrate that the eggshell is gone, is I went ahead and put blue dye, food coloring dye, in our vinegar, and it has changed the color of our egg. So you'll see that almost all of the eggshell is completely gone, with the exception of this little piece right here. But rubbing your finger across it will start to remove the remainder of the eggshell, and you'll get it down to a point where it is completely clean of the eggshell. At this point, we have our egg that has its shell completely dissolved off. We can see the yolk in there very well, and we can see the semi-permeable membrane very visible at this point. We're going to go ahead and soak our egg inside of a hypotonic solution. This means that there are very few solute particles in there, and so we just are going to be having a plain ordinary solution of water. If our hypothesis holds, what will occur is the osmotic process, where the water will actually move through the semi-permeable membrane into the egg and cause it to swell. Here we add our water. And we just want to have enough water in there to cover the top of the egg. With enough water in there, we're now going to leave it to soak overnight, possibly for up to 24 hours, but we should receive results within about 8 hours. Again, we have another egg with its semi-permeable membrane showing with the completely removed shell. This egg we're going to place into a hypertonic solution. That is, we're going to place it into a solution of Karo light corn syrup. This corn syrup is going to be used to allow the osmotic process to occur, but this time the water should flow from the egg, which is inside of this egg, out to the container and settle on top of the syrup. This allows for a movement of water particles from high concentration to a low concentration. So you're probably wondering to yourself, why doesn't the corn syrup move into the egg? Well, because the egg has a semi-permeable membrane, the sugar that's in the corn syrup is actually too large to pass through the semi-permeable membrane. This means that only the water can get out, hence the name osmosis. So we'll place our egg inside of the container, and again, just like we did with the water, we want to put just enough of the corn syrup to just cover the egg. As you can see, the egg is now completely covered, and we're ready to put our lid on this one. So on the left side here, we have our egg that just came out of the corn syrup. It was sitting for approximately 3 days in the corn syrup to allow maximum osmotic process. So what we see here is that the egg is very, very, very delicate and very, very dehydrated. This is because the water that was in the egg has now been left in our concentrated solution of corn syrup and water. And you can actually see at this point, here's where the corn syrup ends, and this is the water that was contained within our egg. Over here on the right, we see our egg that was soaked in a water solution. Now this egg was left in water again for 3 days, and so the water has actually flown into the egg. It's not quite as dramatic as the syrup egg, but it has swollen. If left for long enough, this egg will actually explode outside of its membrane and go everywhere. So we've kind of reached probably the maximum for it, and you can see that there has been maximum water absorption. The next thing we'll do is look at the mass of these two eggs. So here we have our scale, and you'll notice it has a paper towel already placed on it. The reason for the paper towel is to protect the scale from anything that might come off of our two eggs. So the scale actually has to be what we call zeroed out. That means that this measurement from the paper towel is removed from the calculation. To do this, we hit the zeroing button. Now that we're showing 0.0 grams, we're ready to go ahead and measure the corn syrup egg. If you'll recall, our egg earlier had a mass of 60.3 grams. Placing our egg on the scale, we can see a very definite change in the mass of the egg, now being 42.4 grams. Again, we have our paper towel back on the scale. We'll notice that it's beyond zero, so we'll just go ahead and zero it out. And at this point, we're ready to measure our water egg. So now that the scale's zeroed, we'll place our water egg on there. What we can see now is the water egg has increased in mass from 60.3 grams to 93.9 grams. Now that we've collected our data, we're going to go ahead and do some calculations. Here you'll see a table that I've created that shows all three of the important numbers that I asked you to write down from the video. The original mass of the egg was 60.3 grams. The corn syrup egg, the one that was soaked in the corn syrup, had a decrease in mass to 42.4 grams. And the egg that was soaked in water had an increase in mass to 93.9 grams. These three numbers play a critical role in our ability to calculate percent of change, which leads to percent of increase and percent of decrease. To begin our lesson, we first need to understand what percent of change is. Percent of change is a ratio that compares the new amount of information, in this case our new mass, to our old or original amount of data, in this case our original mass. This ratio will be written as new over original. Now, if we want to make this into a percent, we'll need to use a proportion. The proportion that we'll use allows us to put the percent that we're trying to find for the new data over 100. The reason we place it over 100 is the original is supposed to be equal to 100%. That is 100% of the value of that egg. With this basic formula, we can now find the percent of increase. So we'll start by finding the percent of increase in our egg, and that means that we have to look at which one increased in size. The one that increased in size, if you'll recall, is most definitely the egg that was soaked in water. So we'll need the original data for our particular egg. Our original data was 60.3 grams. Our new measurement for our egg, if you recall, and we can go back to our table to find it, for the water egg was 93.9 grams. So we'll place that into our proportion. Then we simply set this equal to, and we'll use the variable p here for the percent, over 100. So we go through our basic process of solving our proportion here. We'll cross multiply. This will give us our 9,390, setting that equal to 60.3, whoops, not G, times P. We have a one-step equation. We do have a process for solving this one-step equation. We want to isolate the variable. That means we'll divide by 60.3 on both sides. Dividing by 60.3 on both sides allows me to cancel this set, leaving me just the P for the percentage. Now 9,390 divided by 60.3 yields what we call an irrational number. So what we're going to do is round this number to the nearest whole percent. It turns out that the number is 155.7. That's all we'll really need to round to the nearest percent. Since we're rounding to the nearest whole percent, we look at the number next to the 5, in this case the 7. Since it's greater than 5, we'll round this up to 156%. It is important to note this is not the percent of increase. This is simply the change, percent of change. Now to find the percent of increase, we'll need to take that 156% and we will subtract the original 100%. By doing this, we're only looking at the amount of change, or the percent of increase. This takes into account the new percentage compared to the original. Once we do this, we can easily see that our true percent of increase is going to equal 56%. So since we've looked at percent of increase, now we'll want to look at percent of decrease. To do this, we'll use the same formula. Now if you recall from our data table, our original value again was 60.3 grams. Our corn syrup soaked egg decreased in volume to 42.4 grams. Again, we'll set this equal to P over 100. We'll follow the same process we used the last time with the proportion. This gives us 4,240 equal to 60.3 times P. Again, we'll divide both sides by 60.3. Doing so allows me to cancel this side. And again, P is going to be irrational. This time we end up with 70.3. Again, we're going to round to the nearest whole percent. So we look at the number to the right of the 0. Since it's less than 5, this means we'll end up with about 70%. This also is not the percent of decrease. This is actually the, again, percent of change. In this case, we have to do it a little different than last time. We'll take the 100%, which was the original, and this time subtract it from the new value, which is 70%. And these were both percents. This gives us our new value of 30%. And that is actually the percent of decrease. I hope that you have found this video educational and informational. Thank you.